Hey there, Internet. Did you ever wonder what a Gerber file actually was? Well, this morning I had to find out for myself. This is easy EDA, where you start with a schematic, you turn it into a design with some traces on it, and it figures out like how to space the copper and do all this great stuff. Then you import this thing into something that'll convert it to G code. And in my case, I'm using this thing called FlatCam. And FlatCam will basically process the Gerber file and magically translate it into a set of G code for a CNC mill to go do. But I had never really understood what Gerber was. I just knew it was a thing that you use for PCBs. Now, many years ago, I saw this article, not many years ago, many years ago, 4 years ago, I saw this article on Hackaday where you could use these expanded shapes to make milling PCBs a little bit more straightforward. So I was working on another project, and for some reason I saw this again, and I downloaded this paper, and I was reading this paper, and this paper proceeds to describe how difficult this problem actually is. And I didn't realize again what the Gerber file was, but essentially what it's describing in this paper is basically a bunch of flashes from a photo mask, this thing called a photo plotter. So I thought I'd maybe dig into this and explain the history of the Gerber file and the history of the photo plotter, because it was kind of news to me. I didn't really understand how it all worked, and I thought it was kind of interesting. We should start with the problem space. And if you've ever made anything with wires and you haven't used a PCB, you are probably going to make a giant mess. Like, here's a great example of something that's just an utter nightmare. And I figure, like, just imagine that something goes wrong in this, something breaks. Like, what are you going to do? You're totally screwed. And if you sneeze, you might disconnect one of these crazy connections. And this is just an absolute mess. This thing here is not that complicated. But when they started to get into making computers, there's kind of like an exponential growth in the connections required, right? The next alternative that people discovered was this thing called wire wrapping. Here's like an example of somebody who insanely went through and wire wrapped all these connections. And you can see it's still a god-awful mess, right? This is kind of a big problem. And that's why we have PCBs. PCBs are a way that you can avoid a big part of this mess. You can do single layer PCBs. You can do multi-layer PCBs. So here's an example of an early PCB. Pretty straightforward. You can see that a lot of this was very highly manually done, and they needed a way to do this in a much more automated way. You can't handcraft all these PCBs if you want to do anything at scale. One of the first uses of PCBs was to make these proximity fuses. And if you can imagine, in World War II, they made a lot of these. And so this is where the scalability of the PCB in manufacturing starts to become apparent. If you need to make millions and millions and millions of something and it's electronic, you're probably going to need to make a PCB. Here's an example of a 12-layer PCB where you can make lots and lots and lots of connections, and there's not really any chance that you're going to sneeze and break a wire loose. So that's why we have PCBs. PCBs are in everything. If you have anything electronic, it's going to have a PCB in it. The way most PCBs are manufactured is pretty straightforward. So you coat the PCB with something, and that something will basically prevent certain parts of the PCB from being etched. Then you basically dip it into something that'll eat the copper away, and it'll selectively only eat certain parts of the copper away. And when you're done, you're left with basically a bunch of wires that are attached to some kind of substrate. That makes it so that you can do this at an incredible scale. You just need a big vat, and you just dunk all the PCBs in the big vat, and you wait for a little bit, and basically the copper gets eaten away, and you're left with the wires where you want the wires to be. You drill some holes in it, and off you go, right? Now, you can do this by hand. It's pretty straightforward to do it by hand. If you're going to manufacture PCBs, you need a little bit of a different setup. At this point, Paul Eisler comes into the picture, and he basically invented a way to automate a whole bunch of this stuff with respect to the photo masking and how to do this at scale. The photo plotter is essentially a robotic light that shines light down onto some kind of a photoresist, and that will essentially make the covering onto the copper layer. When you dip it onto the etchant, you'll be left behind the right traces for what you needed. Now, these machines were fed by magnetic tape or punch cards, and they basically just got a bunch of coordinates to figure out where to shine the light, when to open the shutter, all these sorts of things. In order to program these things, the Gerber file format was invented. But here is an actual Gerber file that I generated from one of my projects. And the standard for this file is called RS274X, which is a derivative of RS274D. Now, you may be asking yourself, what is RS274D? And what you'll find out is RS274D is the G-code standard, which is kind of interesting. I didn't actually ever realize that. So this is the instructions, a set of vectors to basically tell the mechanical light shiny thing where to go and for how long to shine a light. It's also interesting that a very similar technology, which is photolithography, is how they make CPUs. Lots of little tiny wires. They're also including transistors in that process, but I think it's also very interesting that similar to making PCBs is the process of making CPUs on a much, much, much smaller scale. Thanks for coming along on this journey of a rat hole into Gerber files and G-code. If you got any comments, leave them down below, and thanks for watching.